Manufacturing at IISc Bangalore. My additional role is a guest assistant professor in electrical engineering at IIT Gandhinagar. Since this was the first template I used PPT, other things are a little bit different than the regular template. Next 40 minutes, I'll be talking about some of the technologies that we are working on in the lab. And just a quick brief bio. You're able to hear, right? Sai Siddhant is saying that he's not able to hear. I hope I'm
You're
audible.
quite clear,
Yeah,
sir.
No, sir, your voice is audio.
Okay, thanks. So just to quickly give my brief bio that right now I am leading three different laboratories in this department, and I have my PhD from IIT Delhi and multiple postdocs from Maryland and one from Harvard Medical School. So let me go to the next slide. This is the institute. Most of you know about IISc. Our just people who don't know about IISc, it is more than 100 years old institute, and fundamental focus is on research and training. We only have a postgraduate program. Recently, we have a new undergraduate program as well. But like I said, primary focus is on research and development. I'm one of the 500 faculty member who are working in this institute. And as far as the laboratories are concerned and the research areas are concerned, so my research lab works on several different research domains, right from cancer research to brain physiology, catheters, infectious disease, cardiovascular tools, non-invasive technologies, and we try to develop as many sensors as possible indigenously. When I say that as many sensors as possible is the reason because if there are already miniaturized sensors which we can directly use it, there is no point of reinventing the wheel, and thus we work on sensors which are not available for particular application, and some of those applications we'll be discussing today. I'll go through a video which shows that what are the research facilities that we have in the department, and these are some of the organs that we work on. Right from brain, we work on the Parkinson, stroke, epilepsy, all implantable devices. We work on neonatal hearing screening that we'll talk today. We work on breast screening and diagnosis sensors and technologies, liver cirrhosis, where we work on non-invasive technologies. We work on the cardiovascular diseases, including congestive heart disease, bacterial inflammation, dehydration monitoring for kidney, biosensors for understanding different kind of proteins present in urine, in saliva, and in nodes. We also work on oral cancer cytology scanning system, and some of the sensors and biomedical devices are shown in this particular slide, although it is not a complete coverage of what we do in the lab. Now, when you work on healthcare, does not mean that the sensors are only focused on healthcare. It can be used for other applications, including agriculture and other things. But since today we are going to talk on healthcare, let me show the clinical collaborators. And these are the clinical collaborators that you can see on the screen. I work with nephrologists, cardiologists, oncologists, neurosurgeons, ENT surgeons, neuropathologists, and neonatologists. So about 32 different clinicians work with us, and thus the important problem in the area of healthcare comes to the lab, and we try to solve those problems by developing medical devices. Medical devices, when you talk about, it can be diagnosis, it can be screening, it can be assistive devices, as well as it can be devices that can be used for curing. The primary focus in the last 8 years at IISc is on developing this screening and diagnosis technique, and now we are moving to the other side of it, where we want to treat the patient as well. All these devices includes a lot of sensors, and we'll talk about some of them today. This is a video of the lab. I hope that you can see the video. Okay, so I have already shared the link for the entire presentation, and all of you can look into the presentation and the slides. If you have any questions, you can ask me. This was just a video to showcase what we have at IISc, and as an academician and also a faculty at IISc, I invite all of you to see if there is any possibility of collaboration when the project or research idea is cutting edge and innovative. Of course, some of the facility I am okay to help you across all the participants, including the organizers, if you want to take advantage of these facilities at IISc. When I say at IISc, particularly I am talking about my labs, and of course there are different facilities that we can use it in the institute, but I'm not showing it as of today. So coming back to today's presentation, I'll be talking about, you could see in the video that there are so many sensors, so much of applications, electronic modules and other things, everything and anything that you see, except we have to still import the silicon wafers, right? We have to still import some of the ICs, some of the components, right? But most of the things other than that, it is indigenously developed at IISc in our country. Now, what we'll be talking today is four different topics, and we see that how sensors can play an important role in those four applications. The leftmost photograph here you can see is a non-invasive technique to identify liver cancer or liver cirrhosis. How we can do that? By understanding the signature present in the breast. Then on the right side, top right side, you can see a photograph of neonatal hearing screening. Here we'll talk about the EEG. EEG stands for electroencephalogram. Then we'll talk about on the left bottom image, you can see a multiplexing or multiplexed biosensing technologies. You can measure different proteins simultaneously. This is example of saliva, but we can use it for blood, we can use it for urine and other examples. It's a whole multiplex system, so it's a portable in nature. And the right side of the slide, bottom right, is a sensors or implantable neural implant that we have fabricated here, and we implant it on rat's brain. This is to study the Parkinson and also to understand how electrical stimulation can help in improving the Parkinson traits. So how to solve this issue of Parkinsonian? We take with the rat model and then we go towards human, but here we'll focus on rat model. Okay, so let's start. The first topic in this one will be on non-invasive neural engineering, on understanding neurophysiological signatures. When I talk all these things, it becomes a little bit difficult. To make it very simple, let us go to the next slide and I'll play this video. And I hope that the audio in the previous video was audible. The sound was audible? Yes, yeah, great. Okay, thank you. So I'll play this video. Listen to that.
ನಿನ್ನ ಹೆಸರು ಏನು? ಒಂದು ಎರಡು ಒಂದು ಎರಡು
ಒಂದು ಎರಡು ಮೂರು ನಾಲ್ಕು ಐದು
ಶಾಲೆಯ ಹೆಸರು?
ತಟ್ಟ ಟಿವಿ ದತ್ತಿ ರೋಟರಿ ತೀವಾ.
Okay, so if you all of you can hear the audio as well in the video. The first child was asked to speak 1, 2, 3, 4 and name in Kannada, which is the state language here in Karnataka. And she was not able to speak clearly. It was like 1, 2, 3, 4. And the second girl, as you can see in the video and probably you can hear, she was able to speak very clearly. Both these girls were having a hearing deficits when they were born. The second one was intervened at earlier stage. The first one was intervened at a later stage. And you can see a very clear differentiation between both of them in terms of speaking. That is, speech is correlated with hearing. And second, also researchers have found that cognition is affecting or is correlated with the hearing deficits. So earlier intervention, better hearing will have better cognitive abilities and of course better speech. Now, why to work on and what is the gap here, right? One, of course, that early intervention is important. That means early screening is important. So are we not doing screening? There is a very clear mandate in government saying that all the newborns have to go through the hearing screening test. Now the cost for so how it is done, you apply a audio stimulation through the ears, and you measure EEG signal from the forehead, as simple as that. But there is a limitation here because the cost of the system, which we call as a bera, is the name of the equipment, uh, the cost is about 14 lakh, 1 4 lakh. None of our primary health centers, as I am speaking today, has this system, right? And about 70,000 babies are born every day in our country, out of which 40 to 35 to 40,000 are born in villages. For every 1,000 babies, 5 babies have hearing deficits. And if they're in ICU, then out of every 100, 2 to 4 has hearing deficits. So if you take the numbers are huge. And in villages, when the babies are born or where the primary health center is there, since the screening is not available, the parents will only know whether baby can hear or not when the baby is about 2 3 years old. So early intervention is not there. So the question is, can we develop an indigenous headband that can be used to screen the babies in primary health centers? That's the first question, right? And the second is, it should be affordable. And third thing, it should be easy to use. But also, is there any science that we can bring it along with just developing some technologies? So there is something called uh, mismatch negativity. If you see this particular slide, here from the outer ear, how the audio signal travels to the brain, right? It from outer ear to cochlea to the cochlear nucleus to the auditory thalamus, and when it reaches auditory thalamus, that is what ABR is, which stands for auditory brain response. If it reaches this particular auditory thalamus, it is what's the audio stimulus. Then you can see all these 7 peaks, particularly peak number 5 is of importance. Okay, so this is, if the peaks are present, the doctor will say, okay, baby can hear, as simple as that. But in some of the cases, even the all these peaks are seen or visible, the baby or newborn cannot hear. In that case, they cannot hear because they are cortically deaf, right? So to measure or not let these kind of cases go away, we have also introduced one more thing called mismatch negativity, where this audio stimulus will travel further from auditory thalamus to the auditory cortex. If it reaches auditory cortex, you can see a very clear visible biosignature. So what is that? It is like da 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 da. There is standard and deviant. The deviant is a higher pitch that I have just used, right? And if you can do that, then you can see a very different biosignature, as you can see in this particular figure, where my arrow is there. There is a deviant and standard, and you can measure the mismatch negativity. Why it is important? Because it's an early biomarker present when for a newborn, right? The bone is not completely fused, so there's a higher signal. That is what we call as a open anterior frontale. The bone is not completely fused, and that's why there is an advantage of current leak and higher signals are present. So we are adding not only ABR but also mismatch activity to not only screen the babies who have hearing deficits, or some babies who are really good in terms of auditory thalamus, reaching the stimulus auditory thalamus, but they cannot hear because of the cortically deaf, the auditory cortex it is not reaching. So adding two signatures, ABR, auditory brain response, and mismatch negativity is the science that we bring in along with the headband with the things that I was talking about. Now, these are some of the systems. There is also a Indian company, Soham. The system is also really good. The only difficulty is that it requires multiple people to put it together and use it. The idea is not to put in only tertiary clinic. The idea is to reach to primary health center, where the people or the what we call as a asha worker or primary physician, they are not trained, they're not audiologists, right? So someone who is semi skilled or minimally skilled can also use this kind of band. It will just show red, yellow and green, as simple as that. Red and orange or red and yellow means baby cannot hear, green means baby can hear, right? If the baby cannot hear, you take the neonate. For neonate is within first 30 days, okay, or first 90 days depending on the definition. But you can take the baby to the tertiary clinic where further intervention can be there. So with that idea, we developed this headband, and I'll show you some of the results. And the ABR is at higher frequency, about 16,000 hertz, or it's a 16 kilohertz, and the ABR MMN is at 250 hertz. So now we have developed our own indigenous electronic modules that can do both the things simultaneously. When I say simultaneously, it's one by one, but in very few seconds, so the screening is faster. This is the auditory stimulation for different ERPs, and you can see a mismatch negativity auditory stimulation as well. So I'm playing it. This is mismatch negativity. You see the difference, right? So this is auditory stimulus. It is given through the ear. This is ABR. Right? These are different decibels. Of course, the decibels are lower, but I'm just showing it for the understanding of the audience. So these two techniques are there, right? Which are used as an auditory stimulus, and EEG is measured either from one electrode, which is called prefrontal, or the central electrode, and when there is one more. So we can use three different electrodes. Now let me show you the image. This is a blown up diagram, right? As an engineer, we should learn multiple things. This cannot be possible without having people from different engineering domains, mechanical engineers, electronics engineers, UI developer, software engineers, right? So there's a lot of people, and of course the biomedical and the clinicians, right? So this is engineering drawing where you can see that there are different kind of structures. We use three different electrodes. Here we call CZ. CZ stands for central electrode. FZ is a frontal electrode. FPG is a prefrontal electrode. Everything is in the centers. In EEG, if you want to further understand, all the even number of electrodes are on the right side. F1, F2, F3, C1, C2, T1, T2, sorry, I'm sorry, F1, F3, C1, C3, T1, 3, T3, so on. All the even number of electrodes. Odd number of electrodes are on the left side of the brain. 2, 4, 6, like that. Okay. And all the central electrode are marked by Z or Z. So you can see FPZ, FZ, CZ. These are in the center of the head. Okay. So here you can see the band, right? And there are three different electrodes, actual bands on the neonate, and we are able to measure a very clear signature. As you can see here, all seven peaks are very clearly visible. Peak number 5 is dominant peak. We can see in all the cases. We are compared with a reference system to see that how our device or the system that we are developing works. We also do the ERP imaging to see whether when the fatigue will get introduced. Because if you keep on hearing this for a long time, right, then the person will have like the brain will get fatigued. But if we add a signal processing technique like wavelet, right, then we can reduce the number of epochs, number of trials, and we can quickly get the results. So that's the idea of adding signal processing, developing a band, using EEG signal, and understanding and solving a very important problem that exists in front of us. When you want to send the data, all this data you can collect very clearly collect through the EEG. You can quickly send the data to a remote pathologist or remote specialist, audiologist in this case, using IoT, right? But since today is focused on sensors, I'll not touch upon the IoT or AI part of it. Even you have a lot of signatures like this, the AI will further help in understanding, delineating different signatures. However, in this case, there are two signatures which are very clearly observable. That's why AI does not play a role in this particular application. I'll come to the application where AI will be really useful. So MMN also we were able to measure, and ABR we were able to measure. This technology is somewhere at between TRL4 and TRL5, since one of the important thing about the template that was shared with me yesterday was to talk about the technology readiness levels. Here we are at TRL4, 5. You cannot, I'm sure that all the participants today know that we cannot use any of these sensors or any of the transducer or this technology if we are going to place it on human without getting a proper ethical clearance. So it's very important to get the ethical clearance to utilize this kind of technologies and place it or take the data even from the normal subjects, even from the students working in the laboratory, right? As per the ethics, even on myself, right? If I develop something, I should not take it until I have a ethical clearance. Now, a lot of people don't know and they do it. It's very different. But let us follow this protocol. This is the right protocol to follow. Let me quickly give the credit to my clinical collaborators, Dr. Manjunath Dandi from KIMS and Dr. Pratik, who is at Indira Gandhi Hospital. Some patents and publications I'm always happy to share with all of you. So let me move to second topic. I just picked four topics so that it gives a flavor of what we do in the lab. There are 30 projects right now ongoing in the lab. So in 40 minutes, 30 projects will be difficult. Also, a lot of overwhelming thing for the participants. So I just took four which we can discuss today. All right. So the second project that I will be discussing is on biosensors. This is for protein-protein interactions. People have studied antibody-antigen reactions, aptamer-antigen reactions, and so on and so forth. We being an electrical engineer or electronics engineer, we focus on impedance measurement, in particular, how to create this kind of biosensors. The idea was instead of putting the samples individually, can we just put sample one time and it will spread across four different or five different wells, and you can measure the presence of protein in all five wells. Now the whole question is, what is the gap and why we want to measure all these proteins, right? Now generally what happens is, during the intraoperative surgery, the surgeon will remove the lymph nodes. Lymph nodes are crucial, you know, parts. I will just put it in a very simple language, which are useful for improving the immune system, or which helps in the immune system development or to keep immune system active. Now if you remove the lymph node, the immune system will get deteriorated, right? It will get affected. For during the intra surgery, these lymph nodes are taken and sent to the pathologist to check whether lymph nodes are affected, whether the cancer has been spread to other parts of the body. In some cases, the lymph nodes are not affected at all, but once you remove, you cannot place it back, right? In the human body, it's very difficult in any animal per se. So can we develop a sensor that can tell whether the lymph node has been affected, that means the cancer has spread or not? If the cancer has spread, then based on the literature, we found that certain biomarkers are present, which are mentioned here: CK19, DSG3, ITGA5, DUS10. All right. So if we can take a sample of the lymph node, not remove the entire set of lymph nodes, right, and can do the following study, which is written here, right? Homogenization for protein extraction, phase separation, and then you place this sample on this particular chip. But before you place it on the chip, this chip has interdigitated electrodes, and on these electrodes you can place or use antibodies or aptamers after performing the surface modification. The antibody role is to capture this protein, right? There are two types of antibody: monoclonal and polyclonal. Monoclonal is costly but more specific, that means more selective. Polyclonal is not as good as monoclonal. People have now started using aptamers, which is again a interesting approach. So now if you put this protein or antigen in the center, right, and this antigen will spread across all four wells through this microfluidic channel that you can see here, lines, right? And it goes here, and then you can just connect to our impedance analyzer and we can get the data. Is as simple as that? Not really. Once you load the protein and you do incubate, you wash it, and then you load to this particular impedance analyzer and you can see the data. Now you have a portable system, but we wanted to make it even better, and that's why you can see here. Now what is the advantage of making all these things on PCB? We cannot fabricate microsensors. We have a fab lab, right? We can, but if you make this kind of things, you can make in hundreds and thousands, right? And you can reuse it. Why reuse it? Because the electronics waste is one of the very important area that we have to reduce the electronics waste. So if you place this chip in the oxygen plasma system, the surface chemistry that we have done, the antibodies that were there, the antigen was there, everything will just get detached from this particular PCB, and you can reuse it. All right, that's a whole advantage of making reusable. We can have four wells, we can have six wells, we can have electrochemical sensor instead of electrical sensor if you want to. This is our first prototype where we can just attach and we can just get the data onto the laptop. We have improved upon that. Now we have our own electronics that can do multiplexing. You can see here the entire electronic module. You have 3:8 decoder, 2:4 decoder. There is a multiplexer indicator. There's A:1 mux, power supply, everything within the system. And then this chip is an electrochemical one, electrical one. We have multiple kind of biosensors. We are working on three different projects in this area: one for conjunctive heart disease, one for oral cancer, and one for the urine biomarkers. So here you can see some of the results, and we found that when node positive samples and node negative, positive means the cancer is there, negative means cancer is not there. The DSG3 is present in both, so it's not a great biomarker to look into. However, CK19 is one of the very prominent biomarkers that is interesting and that showed a very different results. We are doing more number of testing. This is in collaboration with Majumdar Saab Medical Foundation, with Dr. Amrita, Dr. Moni, and team. And of course, there are ENT surgeons and pathologists involved in this project. The other application of the similar kind of platform can be in understanding the proteins present in saliva. Right? Can you measure whether some person is suffering from oral cancer? This is a pre-cancer. Okay, means when there is actual cancer, it's very easy to measure. Right? But just by saliva samples, can you measure that somebody has somebody suffering from oral cancer at a earlier stages? Early cancer detection is also very useful because early treatment means more chances of survival. So we found three different proteins there: S100, A7, S100P, and CD44. We are doing testing on this, so I'll not show the results, but I was just showing this slide so that you understand. One more is in the area of the heart, right? So very important, congestive heart failure is one of the very important problem in the medical domain, and there are certain proteins which are present which shows that what stage the heart is, particularly in this area. If there are damaged heart valves or if there is a plague, right, then what to do. So there are different proteins called CTN1, BNP, NT-proBNP. These are the proteins which also the pathologists will look into. They take much more time. We can do it very fast, provided we have a right set of protocols with us and same concept, right? Here the antibodies will be different because antibodies has to be focused towards or specific towards CTN1 or BNP or NT-proBNP, right? That is the only difference. We are also going to we are not also going to we are trying electrochemical sensors as well. Electrochemical sensors have certain advantage over electrical sensors. However, electrical impedance based sensors are faster to use and easy in terms of the analysis. We don't have to do cyclic voltammetry and other things, right? It's very simple. Impedance change, that's what you plot. Okay, so let us move to, and of course, the ethical clearance. As you can see, every project is having an ethical clearance, right? So I have used kind of 25 minutes or so. Let me go to the next application. Two more, and I'll stop exactly at 40 minutes. Try to stop at 40 minutes. So let us go to the next one, which is a portable electronic platform. Also, please do understand that I am an engineer talking medical domains, right? I'm not a clinician or a surgeon. So please ask a question related to engineering platforms, and let's not me feel that I don't know anything in terms of medical technologies or the why something is happening. And I just can say it is there. Why it is there, a doctor can answer it very well, right? So let's go to the next topic. Here we are talking about understanding the liver cirrhosis through breath sample. Human breath, what we are taught, our breath is consisted of carbon dioxide and humidity, and that's it, right? Breath smells good, breath smells bad, and that's what we are generally taught. But surprisingly, the breath is not just carbon dioxide or humidity. It also has lot of volatile organic compounds. And what is volatile organic compounds? The compounds that is volatile in nature, that will like evaporate. For example, petrol, right? A drop of petrol on the table will evaporate. Diesel, kerosene. We don't exhale any of this, so let's not worry about it. But we do exhale acetone, methanol, ethanol, and these are all VOCs, ammonia, present in the breath, but at parts per billion. Parts per billion is an extremely small concentration. Now, researchers have found that for the patient suffering from liver cirrhosis, as you can see, from healthy liver to fatty liver to fibrosis to cirrhosis and then cancer, liver cirrhosis, the patient would exhale breath with a higher concentration of ammonia. Higher concentration of ammonia is from 800 ppb to some few ppm, 1 or 2 ppm. Now, there are current non-invasive screening tools, as you can see here: Ionos, Cryonos, Pen3. I am also sure that somewhere where I was discussing with CDEC, they developed Enos for coffee testing, that what is the quality of the coffee or tea, I think. And this is really good. But when we are talking about sensors that are sensitive at parts per billion, right, then we don't have commercial sensors available. That's why we have to fabricate. Like I said, if commercial sensors at lower cost are available, we should use it. But if we don't have it, like this application, we have to fabricate those sensors. So we try to fabricate sensor, not only sensor but entire system, right? So what we have developed is this thing. This is a leaf sense device because it senses the liver cirrhosis or leaf sense. This is an exploded view of that. We have a piece sensor PCB in which we can integrate commercial sensor. We can integrate our own sensor, and we can use different kind of metal oxide semiconductor material. We can use 2D material. You can use polymers. You can use copolymers, where polymers can be integrated with nanoparticles to improve the sensitivity and selectivity of the entire platform. Excuse me. This is a vacuum system. Why? Because vacuum pump, because whenever you load the breath, right, every time you should have the same kind of environment. So remove all the earlier samples, create a vacuum, then load the sample. So to keep the measurement correct. Okay. Just an example of one of the sensors, which is zinc oxide. All of you are very well aware of zinc oxide, traditional metal oxide semiconducting material. We can also use indium tin oxide. We can use tin oxide. We can use tungsten oxide, and there are plethora of different kind of metal oxide semiconductors. But recent understanding is, if you go for 2D materials or go for copolymers, you have a better sensitivity. Let me quickly play this video so you show that how the system is operated. Right, so a very quick video of how the system is operated, how to load the sample. We collect the sample in toddler bag. Of course, you all know about COVID, right? So to avoid directly using the breath of a patient and a whole system to be is in front of our patient, we collect in a toddler bag and then we use it. We have some inclusion criteria, exclusion criteria. For example, the people who are suffering from COVID or certain disease, they are not part of this particular experiment protocol. We take the readings from control subjects, which are participants who are healthy, and then we take the samples from Aster Medical College because Dr. Sonal Asthana, who is a co-investigator on this project and also liver surgeon, right? He is on this project. So we get samples from Aster Medical, which is in Bangalore. But this is good. And metal oxide semiconductor, you know that the advantage of it is very simple to make. The limitation of any metal oxide semiconductor material is that you need to make it repeatable. Repeatable means that after the VOC is placed inside, there will be change in resistance of this metal oxide semiconductor materials. Generally, if reducing gas is there, resistance will decrease. Oxidizing gas is there, resistance will increase, right? But then it should come back to its original resistance value, which we call as a base resistance, right? We can fabricate, we can make nice repeatable sensors. However, how about we make a sensors which are very simple and affordable? You can just use it and throw. One time use doesn't matter, and it should be really affordable and low cost, right? So for that, we tried and we are trying to make a colorimetric sensors. In this case, instead of using the metal oxide semiconductor, we have RGB sensor that can detect the change in the color of the sensor array, and we can perform the feature extraction and use the pattern recognition. Even the metal oxide semiconductor and other materials, we have to use now AI, right? AI, as all of you understand, right, has different form, different kind of different AI protocols are available. We don't code it, we use it. Why it is important? Because of the data that is there, right? From 500 ppb to 1 ppm, we can have 500, 510, 20, so on until ppm. So many data only from one particular VOC. Group of VOCs, unlimited data. There where the AI would be useful to delineate this particular VOC, in this case ammonia. So in this feature extraction, in this case is a color. Color also is, it can menu means with our eyes we can see something, right? The camera can capture something, but there is much more information in the change in color if you use the feature extraction and pattern recognition technique. We are trying to work upon it. We have been successful in fabricating some of these interesting colorimetric sensors using electrospinning technique, which we are right now using. These are different kind of polymers and these dyes which are there in commercially available, like that means in literature also and in commercially available. So you can use a different concentration to get whatever we are focusing on here. That means this particular device, right? So this system is ready. We are fabricating this colorimetric sensor. At this time, we were able to measure only 2 ppm and above. Below 2 ppm, the sensor was not sensitive. So we are working on improving the sensitivity of this particular array, and the cost of this entire array is close to 50 rupees, and that's it, right? So you can screen, you can change in color, take it out, throw it, and use another one, right? Very affordable and uh, better than most. Although I'm not comparing, that's his own advantages. Dr. Sonal Asthana here, ethical clearance here, and IISc clearance. Okay. Now, with just like 4 minutes available with me, let me go to the last topic on this one, which is the Parkinsonian disease in rodent models. Again, these are invasive technologies. That means we are fabricating implantable device. As you can see here, these are implantable devices. This is a flexible neural implant with electrodes here. You can see 5 electrodes are there. What happens is that in case of Parkinson, if most of you should know, and if you don't know, then I'll tell you that generally DBS, which is a deep brain stimulation electrodes, are used for people who cannot, whose Parkinson is at a higher stage and they cannot be treated with the medicine. For those subjects or patients, the doctors will use the DBS, which is the deep brain stimulation electrode, that goes inside the brain, deeper into the brain. The question that we asked is that how about we fabricate neural implants that can look at the surface of the brain and not go inside the brain. Anything that goes inside the brain will have some kind of damage to brain, right? So can the only surface electrodes would be useful, or can combination of surface plus DBS would be more useful, right? So with that understanding, we started working on rodents. These are rats, and on rats you can see here the motor area. The Parkinson is associated with motor area, right? Because motor area, it controls the hand movement, leg movement, right? And a lot of other stuff. So the point is, in the rat you have this one red color circle is here, same thing on other side of the brain also. So you require to collect the data from here. Are there any commercial implantable devices? Yes. Are they specific for this application? No. So we need to fabricate our own, or we asked and pay a lot of money to this company which is outside India and get it fabricated, which makes more sense to try by ourselves. And that's why we tried. We are successful. We have done a lot of surgeries. And are we in the right area or not when we implant the device? You can see in the video. Please focus on this rat's paw, right? We don't say rat has a hand, it's a paw. So here, all right, where my hand is there when I play the video. So let me play the video. You can see here. See, it's moving, no? It's moving. So you can see that, right? It is moving. Again, I'm playing. You can see the rat's paw. See? Okay. And this is when the electrical stimulation is given. That means when you touch the brain and you apply electrical stimulation, the paw will move. Now, right side of the brain is connected with the left side of the body. Left side of the brain is connected with the right side of the body, right? In this case, it's a left paw moving. Hmm. Same thing here, you can see the EIB platform, electronic interfacing board is EIB. And finally, the rat is happy. Rat is healthy and happy, is moving. Whenever you want to take the data, connect the cable. You don't want to take the data, let the rat freely move in the cage. So we have done all these studies. We have done the impedance measurement of this electrode. This is a motor assessment when you can see that the rat can hold the rod. This is a rod which rotates. That's why it's called rotar rod. And rat holds it for a long time, right? So he's holding still. I'm just playing video faster in interest of time. He's holding, and now it will fall, right? But when you take the Parkinson rat, it will not be able to hold that long. All right. The second test is if there is a Parkinson rat, right, what will happen? You can see here, Parkinson rat, the tapping is less. It is not able to move the paw. You can see. So that means the Parkinson is induced. How to induce Parkinson? By using this 6-OHDA drug, you can insert in the brain and it will cause Parkinson after 3-4 weeks. And then the rat is okay. We are able to take the data when rat is drinking water, right, or eating food or grooming, right. You can see the cable attached here, and you can in real time collect the data. The device is implanted in the rat's brain. All right. These are all the data comes from the rat's brain. Let's not go into the detail, but what I wanted to show it to you. These are all called ECOG. ECOG is electrocardiography. EEG is on the scalp. ECOG is on the surface of the brain, right? So we have fabricated this device indigenously, right from materials all the way to sensor and its application. And thanks to Dr. Shabri Girishan, he is a collaborator and he is also pursuing his PhD with me. He is a neurosurgeon at Ramaya, just next door to IISc. Again, even animal is there. We have the animal ethical clearance. You can see here, right? Both from IISc, because there are two different projects, and of course IBSc clearance. Some of the patents and publications. Thanks to the funding agency, almost all the funding agency that I go, very kind. Not because of just IISc. A lot of proposals were rejected also when I started. Over a period of time, we understood how to put the proposal together, how to present it well, what's a gap that we need to address, right? How much interesting is from the translational point of view. Having said so, whenever I have or whatever sensors we fabricate here in the lab, right? Although I have shown only for healthcare applications, they can be used for several different applications. Okay, so don't limit your understanding that sensors can only be used for one particular application. Let me go to the last slide, which is my thank you slide. Here you can scan this one and you can go to our lab, right? Understand what we do, and my details are here, right? You can again contact me if you have any pertaining questions to this particular proposal. So thank you once again. I again apologize for the delay in sharing the PPT, and very quickly, if I can take one or two questions, I'm okay. Otherwise, if the time is not permitting, we can connect offline.